for big data at the speed of thought. So how many here are already using Spark? Show hands. Okay. So before I get going, let me just talk about who we are. How many here know Pivotal? So we are a spin-out. We were essentially created, incubated inside Pivotal, which is essentially a company within the EMC umbrella. We built essentially an in-memory database within the Pivotal family, EMC, VMware family, for almost a decade. Essentially ran a whole bunch of financial services companies, media companies, all sorts of industries, about 1,100 clients. And it was through a lot of experiences we gained building an in-memory distributed OLTP database that we decided saying, listen, we got to learn from our experiences and see how we can adapt ourselves to the analytics world. And it was all about, when we built our OLTP database engine, it was in memory, right? So it gave you very, very high concurrency, high speed, with low latencies. And we built it such that at one point we said, hey, we use Hadoop as a storage layer, and lo and behold, we said, hey, SQL on Hadoop, it's in memory. I should be able to use analytics at a very, very high speed. And the truth is that just because it's main memory, it doesn't really give you that performance. Right? You really have to think about modern day CPUs, how to organize data. So a lot of experience gained through potentially a number of failures that led to Snappydata. So it's actually funded by Pivotal, General Electric, and there's a third investor. So we've been out of Pivotal for about 8 months now. So it's a company that's pretty new. There are about 30 engineers based in Portland, Oregon. So with that, let me give spend a minute or two on level set. What is it that we're trying to do here? Right? So as you guys know, Spark is a compute engine, right, that works with many disparate sources and also works with disparate databases. The key question becomes like, if I were to start using Spark in a much more real-time environment, does Spark with its current model really keep up, right? And as you probably know, Spark essentially, when it comes to its state, it's ephemeral, right? Anything that you essentially store in Spark's cache is immutable in nature. Every time an application comes in, submits a job, unless and until you're using Mesos or YAML carefully, you land up essentially getting your own driver instance. The driver essentially spins up its own executors. So you really rely on some external source to share your data, right? So that's interesting, right? It works really well if I'm running a whole bunch of series of map-reduced jobs. But if I want to really look at it as if it's an operational data environment, right, where any number of applications are coming and sharing that same data, it becomes rather very challenging. Right? You'll end up copying data sets over and over again into Spark executors and creating many copies, working with stale data, that sort of thing. Right? So how do we change? We're changing this picture by literally turning the Spark cluster into an operational database itself. Right? So that's our key mission, right? So if you look at this picture, what we land up doing is Spark jobs. Could be any native Spark job, or more predominantly, we think the clients would be SQL clients, clients could be Java, Scala, Python clients, and they're accessing data. And we land up essentially managing our state by working with Spark's block manager itself, right, directly in the executors. And the way we do it allows, I'll get into some of the details here, but it becomes a fusion, essentially gives you a hybrid database that's capable of both OLTP as well as being able to run analytical queries. So you can essentially do distributed transactions, we give you mutability inside Spark, we allow you to do point lookups, deletes, updates, and as you guys probably know, SQL and Spark SQL is kind of crippled, right? It's all about selects. You can't really do an update, you can do an insert, you can update an index, you can update a view, on and on and on. Right? So one of the things we've done is by fusing essentially what we built in SQL as a SQL database, we essentially extended Spark SQL so that it looks much more compliant as a SQL engine. Right? The other thing is that Spark is fault tolerant, not HA. Right? As in, like, if I have a failure in a Spark executor, I mean, your you'll land up depending on Spark's lineage to get your thing up and running. But that doesn't really work in a real-time environment where a client essentially ran a small operation, and you have to be able to sort of detect a failure and switch to an alternate very, very quickly, literally in milliseconds. So HA is something we'll end up doing, including replication across geographies. We provide persistence essentially, so that anything that is storing in main memory will land up into local disk or land up in HDFS. You can do backup recovery. Right. I'll touch on this. I'm spending most of our time today with this relatively new area which we are innovating. We use the term synopsis data. The other academic term for that is approximate query processing. So I'll be covering that. So this is sort of the focus I was going through. So most of my, hopefully, most of what I'm going to say is going to be around how is it that we enable interactive analytical query processing with higher speeds than what you can achieve just with native Spark, even when the data is completely cached in Spark. So I'll first go through sort of what we have seen with Spark SQL. How many here are using Spark Protocol? Anybody's tried it out? A couple of you. So I'll sort of cover sort of this progression that we've seen in Spark Protocol. Why is it that Spark Protocol is, in some respects, it's 3x, 10x faster than what we see in Spark today. But we still think that in-memory analytics is actually challenging. Why? I'll touch on our solution, right? And then I'll focus and give a demo on the Synopses data engine which we are building out in Snappydata. It's based on sampling technology. So here's one thing, right? I mean, if you guys have questions, feel free to inject because that allows me to get a feel for where you guys come from. Right? All right. So Spark data frames, I guess you guys, most of you know this. It's a distributed, collection of data organized as named columns, very similar to what you see with the same concepts that you see with R and Python and data frames. But obviously in Spark, you get richer transformations, optimizations. And obviously, a data frame can essentially be sourced from any number of sources, right, that Spark supports today. It's a fairly extensible thing, so you can keep adding sources if you want. But what I'm trying to highlight here is that whatever you do with data frames or whether you do with SQL, it lands up essentially trying to create a plan, a logical plan that then turns into a physical and an optimized plan. Right? Optimize and Spark is very limited today. But really, this is what is happening. Right? I'm just showing you a simple query that says if I were to do an aggregation with an average, and I'm doing a group by and a filter, you essentially have an operator chain like this, and Spark essentially goes and does all this lazily. Right? You guys know that. Right? So let's take a look and say, is this really fast enough with Spark 1.6? Right? So a simple query, right? I mean, it's an aggregation that says, hey, give me an average over a data set that is in this case about 105 million records. And I just ran this on my laptop, right? So you got 4 cores, enough RAM to do all this stuff, all in main memory. And what you see is you get about, actually this should have been here. It's all managed in Spark memory cache. You get about 2 seconds. And if you're essentially working with Parquet source, files in Parquet and it's sitting in OS buffers, it's about 3 seconds, right? All of a sudden you switch to a query that is a little bit more complex, where it's not just a full scan, but you're actually grouping in data. Obviously, it suddenly flips quite a bit, right? If I go from 2 seconds to 6 seconds, when it's all in cache memory, and if it's coming from your OS buffers, it goes to 10 seconds merely because now all of a sudden you're now landing up copying your data sets from Parquet. You're going through all the serialization, deserialization, the copying that happens in JVM, thing. Right? So to us, it's for 105 million records, a single query, a single user, right? I've given you 4 cores, you swamped all the cores, consumed about 6 seconds. Great enough, right? And if you look at the plan, I mean, it looks something like this, right? Where to a great extent, I mean, if this is just a plan for the average query, right? So you start with a partition RDD, and you're doing a scan followed by a local aggregation, right? You're doing an average. So every partition essentially is saying, okay, let me compute an average myself, and then all these partitions are then shuffling so that I get a final average back out. Right? I mean, in this case, what you see here is that the number of output rows from the scan followed by the initial aggregation is 11 records, and then it follows an exchange operation. Then the final aggregation says here is my average. Right? So what you'll find in a query like this is that almost all the expense is simply right here. Right? The scan followed by my local aggregation, which should generally be cheap, because you're only outputting 11 things across my partition. It's relatively very cheap to do these steps. But still, you're looking at spending whatever 2 seconds to do this on my little laptop, right? Now, so how did Spark 2.0 do, right? What you see right away is that on a laptop for a query like this, an average went from 2 point some seconds to 600 milliseconds. Right? Probably I can optimize it further down by actually having the right number of partition counts. So how come it went so much faster? And if you go with Parquet, it's still about 3 seconds, right? So how many of you have looked at, anybody here has looked at the Spark optimizations at all?
No, there's a new catalyst optimizer.
Say that again.
The catalyst optimizer.
Right. What happened? What was new in Spark 2.0? And so I'll cover that a little bit, but there's quite a few things that I'm not going to talk over. But so if you look at this plan now, what you would see essentially, this is in the Spark UI, right? It'll immediately show you that in the plan, it's actually doing something which is called whole stage code generation. So essentially in Spark, it's kind of interesting and ironical that Spark, when it caches data, essentially it manages its data in columnar form. Right? And for those of you who looked at databases and how do you do analytics really fast, especially with modern day CPUs? If you maintain things in array form, you get dramatic boost in performance. Right? The simplest example could be like, you throw in like an integer array of a million things in a hash map and say run a Java program, Python, whatever, and say let me compute an average. Probably take a second on your laptop. Right? Do the exact same thing, but putting it in an array, you probably operate in about 90 milliseconds. Right? Straight you get 3 orders of performance improvement, again because of how modern day CPUs work. So what has landed up happening is, the Spark was managing its data set in columnar form. The way the query engine operated was that every time it looked for a record, it landed up almost turning into a row and giving it back to the next level. I'll cover that in a second. So it was not so efficient. Now what they landed up doing is that they're essentially generating bytecodes on the fly, and then the JIT compiler is compiling it, and it's significantly faster. So here's the point. There's a good saying that says, hey, if you want to remove complexity, add a layer. You want to improve your performance, remove a layer. Right? Essentially, in a way, that's kind of what happened here. So, what you see here is how a typical query engine does its work, right? Essentially, like what you see in this thing, it's a plan that says a scan followed by filter followed by an aggregate. These are all operators in a query plan, right? And each of these operators typically is built using one or more functions, right? And the moment you have functions and you think about modern day CPU, how exactly do you execute functions? You land up essentially chasing pointers, right? The moment you chase pointers, you're essentially going across all sorts of areas in your random access memory. It's not so efficient, right? So what happens in the code generation is that it essentially looks at this thing and removes all sorts of virtual function calls on the fly, right? As it starts to figure out saying, how do I optimize this query? It removes function calls. It takes wherever possible, uses arrays and variables as possible. So it's highly optimized to literally give it to the CPU and run it as fast as possible. So here's a slide that essentially shows a sense of why in columnar storage things really run fast, right? So it's kind of interesting, right? We have the Moore's law with memory applying, right? Every 2 years, you get sort of memory density is growing rapidly. The price per gigabyte is shrinking. But interestingly, the speeds of DRAM haven't really increased the rate at which the core speeds have gone up. Right? So what you'll end up seeing is that if you go back to the 80s, a single memory access took about 6 clock cycles. Right? Today, even though the densities have increased, the core speed has increased. It takes a whopping 150, actually even more, right? Depending on whether there is virtual address translation or not. maybe 200 clock cycles to simply access the next in, right? And the problem is that if I'm doing analytics, I mean, everything is a scan, right? Everything is an aggregation. I have to walk through billions of things every time somebody asks an interesting, insightful question, right? And all of a sudden this adds up, right? So what you have to do essentially, with, I mean, what happens with columnar storage, I mean, it's not so new. I mean, MTP databases have been doing it for a while, is that you stick everything in arrays and make sure that every time you're iterating, you're essentially walking through those arrays through instructions that you can pass on to the CPU so that the CPU can use registers, L1 and L2 cache really, really efficient. Right? So it gives you dramatic boost, and that's one of the things that's happening, right? So is this really good enough? I mean, you see that, hey, with Spark 2.0, our performance jumped up because of, I mean, essentially the term we use is vectorization to do all the stuff. It jumped up over 3x, maybe 5x in cases, right? The question is it really good enough? Right? So if you look at, I mean, how many times am I doing a simple average, a simple sum over my entire data set? Right? My queries are typically have filters, I have group bys, I have distributed joins. So here's a simple, actually relatively very simple query. Right? It's doing a three-way join on my data set, which is actually only the largest table in this thing is 105 million records. The join table is only 1 million records, right? And I'm actually literally only projecting one column and only one column. And I'm doing a group by and an order by, right? And what you see here is, all of a sudden, sure, it's on my laptop, right? I mean, if you give it more CPU, this will drop. A single concurrent user takes, in this case, it was a good solid 60 seconds to execute this query. And you add 10 concurrent guys, all of a sudden it jumps to about 200 seconds to execute this thing, right? I mean, today the answer seems to be like, hey, why don't you give me more codes, right? I mean, 1,000 or plus. I mean, the more you go down that path, I mean, you're increasing not only your cost of ownership, but as you guys probably know, distributed computing, you add more machines like that in the network. You're quadrupling the potential of potential problems at runtime. So this is just simply showing, what happened here, right? I mean, why did we go from 600 milliseconds to do a scan and an average, and all of a sudden I did a join pretty much with the same data set, and now I'm in the tens of seconds, if not even more, right? So I think some of you recognize this. The single biggest thing I see in Spark is the cost associated with shuffle and the cost associated with serialization. So if you look at any join operation, I mean, you have to make sure that the entire stage completes before the next stage starts. And every time there's a shuffle, I mean, the entire data has to essentially get written out to the file system, and then you put it out of the file system. So even if you land up using TempFS, it's still kind of slow, right? So the other sort of interesting problem, which not too many people sort of seem to recognize, is that there is excessive copying in all these modern-day Java-based systems, right? And I'm just showing you a simple example that says, I got an object through my network, and I want to essentially put it into one JVM, one server, let's say one executive inside of Spark, and I want to make sure it's replicated elsewhere, right? And all of a sudden, what you see is there is first a network kernel copy, then there's a user space copy in the young generation, then there is a from and a to space copy, then you have the old generation copy, because it's a long-lived object. And now, if I want to replicate, you essentially duplicate that whole thing up the stack on the other machine. Right? Look at about 8 copies of data. As the data is coming in at a pretty high rate, I mean, just lots of wasted clock cycles, let alone a network bandwidth. Right? On top of this, I mean, if you look at DRAM today, sure, I mean, the price per gigabyte is dropping, what have you, but the rate at which the data is growing, and some of the cases we're walking into, for instance, in IoT and finance and stuff like that, I mean, it's just a deluge, right? And increasingly you're saying that, hey, for me to draw the right insight, I need to work with more and more data, right? Especially disparate data sets. So yes, I mean, that expense adds up rather quickly. And the second thing we also see is that a lot of folks are saying, hey, guess what? I want to take the right data sets, move it into either my internal cloud or a public cloud, and then I want to run my analytics there. Right now, how do you really move large volumes to the cloud on a daily basis? Even worse, on a real-time basis. Right? So even if I have a sustained speed of 100 megabytes per second, you take about 24 hours to essentially load up or terabyte of data into AWS. So that's why you see that the moment you essentially you have this inflection point where the moment it's beyond like 3 terabytes, it's significantly better to literally produce SSDs in a local data center and ship those SSDs to the cloud provider to say, get the data up there. Right? So I think that's a huge it's a huge problem. Data volumes and the mobility when it comes to huge volumes is a huge challenge. Right? So the big question we're asking is, can we use statistical techniques to really shrink data? Right? Can we understand data distribution patterns? Can we use techniques that the data mining guys have used for a long time? I mean, how many here are data science guys who use sampling and techniques like that? A few of you, right? So it's similar, right? The idea is to sort of say, how can I essentially use techniques like stratified sampling, uniform random sampling, all the other data structures incorporated into Spark, essentially into our database engine, such that we can answer questions significantly faster, yet use consume and manage data that's significantly smaller, right? So the idea here is to say, hey, but there's a trade-off, right? I mean, the moment you start to sample, well, it's like, what you expect? I mean, my answer is not 100% correct. So the question is, can I use enough of the right techniques so that I can give you a very, answer won't be 100% correct, but can I give you a 99% accurate answer with a very high confidence? Because a lot of apps are happy to trade off 1% accuracy to get a 200% speed up. And the other thing is, we look at the simple example with visualization. Right? I mean, I can't really deal with a billion data points anyway. So if you look at the top one, this was using Tableau. This was done at the University of Michigan, right? They used a special technique for how they were doing this visualization. 2 billion data points, 71 minutes to essentially sort of render this. The same thing, if you look at this, it's barely, can't really spot the difference if you make the error rates. And it takes about 3 seconds, and I only work with 1 million data points instead of 2 billion data points. Right? So the point here is that, hey, listen, I mean, oftentimes you can make pretty accurate decisions, even though my data itself is not 100% accurate. Right? Another problem is when you have this deluge of data, whether it's clickstream data or IoT data from sensor events and things like that, it's noisy to begin with. I mean, it's got all sorts of problems with the data, incoming data itself. So what does it mean to be 100% correct? Right? So in some sense, we're saying that inference is probabilistic anyway. So with that, let me just jump into Snappydata. Just give you a little bit of a background of sort of our core product, which is the hybrid database engine that's sort of built with Spark inside. So essentially, it's an open source, it's an Apache V2 licensed open source product. And it's a system that's designed as a single cluster that can do transactions, analytics, and streaming all in a single cluster. Right? So it looks like this. I mean, the way we did it was we built Gemfire essentially at VMware and Pivotal for a long time. Customers, like I said, it's a real-time design center, low latency, highly concurrent, right? So that multiple users can come in and use it at any point in time. And of course, Spark, as you guys know, is a batch design center, very designed for very, very high throughput, right? So it's really a fusion of the two in some sense. It's a deep fusion, so that we realize, OLTP, OLAP, and streaming analytics using a single unified cluster. So here is sort of the high-level view of the architecture that we are presenting to a lot of our customers. What we're saying is, listen, I mean, rather than sort of working with database infrastructure where you're pulling in all the data, how about essentially a middle tier that acts almost like an analytics cache? Right? So the idea is that, hey, I have my Spark cluster that's running, except not only do I have my Spark immutable caches if you wanted to, but you really have the current operation data sitting in main memory, right? You can have, I mean, these are essentially tables where the data itself is manifested as either columns or rows. And then I can have any number of tables that simply are proxies pointing to, external data, right? Whether data essentially comes from an MP database like Greenplum or Netezza, or could be in relational databases, or literally be in files sitting in S3. And I can have reference data that I can pull in from enterprise repositories. But the difference here is that it's not just immutable, right? If my data is changing, I can essentially directly update it inside my Spark layer. Again, it starts to look, feel, operate like what you'd expect from a database engine. There are a number of things we do. I mean, I'm not covering that, how we have essentially extended Spark clustering and the resource management and all that. But the point here is that, I mean, here I have an in-memory compute through Spark, but I can also do fairly sophisticated state management, right? Through Spark, through our layer. And of course, when it comes to the APIs, all the Spark APIs work. Everything is 100% compatible to Spark. We've added a few capabilities on top. And then, and for interactive queries, we can essentially come into a SQL layer. Right? So this is a little bit more detail that says, listen, I mean, when it comes to data, we can manage it as row-oriented data. So essentially, I mean, what I didn't cover is, I mean, how did we build our OLTP database? Right? I mean, any OLTP database in the market, or for that matter, I think almost all the NoSQL products, whether it's Cassandra, Redis, Gem, I mean, name it, right? They're all essentially row-oriented in nature, and they all do a great job if I have a very pointed question, right? I want Bob's record, I want to change the transaction for Bob, and that sort of thing, great, right? Because and for that, you really need a row-oriented database so that I can do hash lookup and I can quickly go and fetch something. But of course, if I'm trying to run an analytical operation, often that organization of data, even though it's in main memory, it doesn't work really well. Right? So what we'll end up doing is that, hey, you know, the choice that you make when you create a tables, it's a row-oriented table or a column-oriented table. And on top of that, we have added indexing to Spark. Then, of course, our Synopses data structures, which I'll cover in a second. Any thoughts, any questions, comments? Yeah.
Can you talk about more on like when you're running a query, like analytical query, is it like query time aggregation, or do you pre-aggregate based on a row, like the way OLTP system works?
No, we don't pre-aggregate, right? I mean, it's up to you whether you want to pre-aggregate it and store it, but we don't. We just figure it out at runtime what the optimized query plan needs to be, and we'll aggregate it at runtime. Because we anticipate that the state will also change. That's the thing. We don't know what kind of queries will come in, and it's a dynamic system. Yeah.
It's some form of the distributed storage here for the index. How do you protect on the multiple machines that are out there running that the index is out of sync?
Oh, so that is a question. If you're doing indexing, how do you make sure that it's consistent? Right? Is that fair? Yeah, I mean, so a lot of things here. We essentially have a transactional, distributed transactional system that's a Paxos-based system that's built. So the short answer is that we would do row-level locking when new essential data items are coming in, or you're creating something, so that we can guarantee an index update and update into a new memory structure where, say, the table itself is absolutely guaranteed to be consistent. And the way it works is, I mean, if you're familiar with sort of any membership-based distributed system, right? So we're very aware of failures in the clustering system, so that we can guarantee consistency. I don't know if that answers the question, but it's like saying that yes, we do take care of a number of failure conditions that might happen, so that we can guarantee that if you're maintaining an index, it's absolutely consistent.
The NPPDB and the RDB, what's the difference between those two?
Right, an RDB here is like saying, you know, MySQL, Postgres, Oracle, or whatever. Right? An NPP database would be like Netezza, Vertica, Greencloud database. So databases that are built to run sort of analytics really efficiently.
So when the data architect, when they are designing the tables, and so they have to make a decision whether this table is a row format or a columnar.
That is correct. Today, you have to make a decision. I mean, I can cover that. But you make a choice to say, hey, do I want to keep my table in a row-oriented form or a column-oriented form, correct? Right? So you have to have some understanding of the workloads you have. But we are trying to get away from that in the future, so that you just create the tables and we figure out what to do. Yeah.
What type of indexes are you supporting? Column-based and row-based indexes.
Yeah, so I mean, it's a skip list-based index mechanism primarily that we use for the row-oriented tables. The column-oriented indexing is different. I mean, what would I mean, you kind of build delta trees. I don't know if that you know, the term rings a bell. But essentially we maintain in what fashion do these columns are changing. And there is a delta buffer that sits on top of the column store. Right? So we use that to essentially do index maintenance. Essentially we allow, even though you have a column table, we absolutely allow fast writes to come into any column tables. Right? So as the writes come in, we essentially build up what, delta trees. To manage that.
When you choose a table that is row-based, the indexes are only row-based, right?
Say that again. Sorry.
When you choose a row-based table, the indexes are only row-based indexes. You can't create a column-based, columnar-based.
That is correct. Yeah. I mean, the point behind that indexing is that it's an ad hoc lookup, right? I mean, you have some keys you're looking up, or you're doing a range scan, and that's when you use the index. So yeah. I mean, even though it might be a stiplet, it's like really a tree-based organization.
If I say I issue a query, try to join two tables, one from the HDFS, one from the MPP. So where does the join happen? Does it happen in the Spark, the executors, or does it happen in the MPP?
So the question is, what if my tables were sourced? One was sourced from HDFS, one was sourced from some other database, right? An MPP database. I'm trying to do a join. Where does the join happen? It happen actually in the Spark layer. So the only thing Spark supports today is that it can do predicate pushdowns. So it comes down to the connector itself, by the way, right? I mean, if you look at like Cassandra as a connector to Spark, it supports, the Spark's essentially, the query engine in Spark is called Catalyst. It's a fairly extensible query engine, right? So you can essentially, if you have your own database, it's fairly straightforward to build a connector. The only thing you can do is to push down a predicate down into that layer. Right? So the Spark, essentially, the engine will act as the query federation engine. So the join actually will land up happening in Spark. So that's one of the things we're trying to position here, saying that, hey, listen, I mean, quite often with Spark, given that it's just a compute engine, you keep on going and fetching massive quantities of data every time you're running a query back into the Spark here. It just is very, very inefficient. And it's just not the right thing to do. And that's why we're sort of saying, what if we made the Spark memory manager itself look much more like the database? So you essentially are moving all the operational data right into Spark, manage it in Spark, all your queries start to run significantly faster. And I'll show you exactly. Yeah. Any other questions? Good questions? Oh, okay. Go ahead.
Have the local persist.
Oh, local persist, yeah, right. So yeah, it's not connected. I thought there were too many lines. Yes, the local persistence is merely our own database persistence, right? So it's an append-only persistence store. I mean, with compaction, right? I mean, are you guys familiar with Cassandra or those products? So the idea is that, hey, if at all I'm using disk, I mean, you never want to sort of start seeking on disk, right? So that you can really operate even when writes are coming at a high rate, you want to give the highest possible throughput. So the way it happens in main memory databases, by and large, whether it's SAP HANA or MySQL or what we do with Snappydata, or for the matter even Cassandra and even in HBase, right? So you keep on appending essentially to your local file system, right? Each node essentially starts to keep on appending. Even if it's an update, it's actually an append into files. And then lazily you start to compact those files, right? So significantly higher throughput rates. So the same design standard. Was there one more question? Yeah.
Can you talk about the scaling up scenario? Like, what is the cost of I'm assuming you have to reindex and reshuffle in the data, right?
When you say scaling out or scaling up?
Scaling up.
Yeah, I mean, scaling up typically would mean that, hey, I'm going from a 4-core machine to something bigger.
So like intro more machines added in.
Well, yeah, that scale out, absolutely. The way scale out would work is that you rebalance the data, right? So it completely depends on how much capacity you're adding. So if you, let's say you have 100 gigabytes in a cluster, and you give me another 100 gigabytes, it's like saying that, hey, to get a perfectly balanced system, I have to move half the data into the new cluster. Right? So yes, you will pay the price, but it's all pretty fair in the sense that we have patterns of them so that you don't land up actually having to like just do a lock on the system while it's trying to be balanced. Most of the clustering databases do that today, essentially expand that. So scale out, which is kind of the term when I'm expanding the cluster size, would be a relatively non-intrusive operation. But if you scale up, it's like saying I want to move my data into some other machine, in a higher class machine, so you have a much bigger penalty. All right, let me keep moving. All right, so this is what we are saying with our product. It's faster actually. I mean, the interesting thing is that even though you can do point lookups and all that sort of stuff, which you can do in Spark, right? I mean, you can't really, like I said, you can't say, my key is Bob, fetch me my record, right? In Spark, we did that. It has no idea. It essentially scan your entire table to the entire data frame to fetch you Bob's record. In our case, well, Bob is keyed. I know I can hit an index, immediately I can return back, much like the NoSQL or OLTP databases. That's not the only thing. Of course, that is like any number of orders of magnitude faster than what Spark can do. But what we also do is for even plain straight up Spark workloads, write a number of things so that it's faster. The first thing is that like some of the vectorization changes in Spark Proto, what we at least realize is that it's not done. It's done 70% of the way there, not 100% of the way there. So. And by fusing our database, we landed up essentially doing a lot more vectorization, a lot more code generation than what Spark Proto does. That gave us a huge boost, especially for scan-oriented operations. On top of that, I mean, we have, because we support keys inside of Snappydata, right? So you can have a primary key, you can essentially say, hey, it's related to this table. So table relationships, we kind of listen to table relationships and we can co-locate data sets along relationship lines. So that basically means if I'm doing a join, and it is in fact a natural join, which basically means I'm going after keys, then we don't have to do any shuffle. So that also gives us a significant boost. So co-location, less copying, serialization, better vectorization. So use much faster speed. We use less memory. That also is similar in Spark. I mean, Spark uses compression when it puts data in columns. So we have that same compression, and of course we get tremendous compression because of synopsis and sampling if you just landed up with that. And then more flexibility for us is all about Spark, right? I mean, so all the APIs, the ecosystem of Spark is just growing so phenomenally, right? I mean, every vendor is trying to make sure that it's connected to Spark. So it all starts to work that way. So it's deeply integrated, 100% compatible with Spark. We have those extensions, like I said, for transactions. We also have extensions so that when you do Spark streaming, today, with Spark Proto, that was one huge plus in Spark Proto, right? I mean, streaming really caught up, right? I mean, if you do, I don't know how many guys have used Spark streaming on? So Spark streaming was, in a way, not flexible enough with Spark 1.6, right? With structured streaming, essentially a lot more flexible in the sense that you can start operating on windows as if they're tables, use queries on windows and all that, much more efficient. So on top of that, we essentially allow you to do SQL, essentially continuous querying, doing streaming. Anyway, so I already covered all this, right? I mean, you're doing an OLTP and OLAP store, and it's row and column, and it can be main memory only, it can be at disk. The SQL is not more compatible, right? So here's a quick view into TPCH, I mean, TPCC, TPCH, I've heard about those benchmarks. With TPCH, we go, I mean, it's a range of queries, right? You can't see, but for a number of queries, we are anywhere from 2x to like 20x faster at TPCH, for TPCH queries. And for, of course, point lookups and stuff like that, we don't even want to do comparison because it's unfair to Spark. Right? All right, so let me just jump into our Synopses engine. I'll rush through a few ideas, concepts here. So the first thing is that if you look at the table on the left, it's got about 6 records, right? It's simply trying to say, do I add analytics? So I have an advertiser from a particular geography, where was ad displayed, and what's the current bidding price for it, right? Simply 4 columns. And if I take what is called as a uniform random sample, and I say my sampling rate was a third of the data, right? I could have picked up these 2 records, right? And if I run a query like that, where the geography was not New York, but some other state, well, I have nothing in my sample, get a 100% wrong answer. So this is quite common, right? I mean, when you do sampling, you say essentially, most people, it's pretty simple to create a sample, right? So, well, how do you address it? Well, you make your sample larger, right? So if you make your sample larger, I mean, the problem is that all of a sudden, you're consuming more space. I mean, the queries that you're running are taking more time, right? So, and the other problem is if I, let's say, increase my sample from a third to 2/3, right, my sampling fraction or the sampling rate. So yeah, sure, I might have picked up a record here, right? But still, given that I have only one for that state, I mean, my error rate is still very high. Right? So the answer to that is, instead of doing uniform random sampling, you do stratified sampling. You guys know what, who knows about stratified sampling?
Question.
Yes.
The previous slide, you said having a larger uniform sample rate, the error rate is just high.
Yeah, the problem is that, in this example, you landed up picking only a single record, right? So of course, you can keep on increasing your sample size so that your error rates keep on dropping, right? But at some point, see, the point behind all this is that in real life, if you look at dimensions, like in this case, the dimension is geography, right? I mean, there are a bunch of dimensions. You have long tails, right? I mean, you essentially have some dimensions in which there's a lot more data, right? And a whole bunch of dimensions where it's very low, has very low representation of real data, right? And the key idea behind stratified sampling, which is sort of the problem it solves, is to guarantee that all stratas, and in this case, strata being this dimension called geo, New York and Massachusetts, Virginia, whatever, I mean, all stratas have nearly good representation in my sample, right? So the idea, essentially, what you see here is that if you look at New York, I mean, I have a lot more records in New York than this guy, right? So essentially, I landed up sampling less for New York, and I landed up having sampling rate for this one higher, right, at 50%. So the idea is that now, if you look at my query, it starts to run, and produces better results without having to actually consume more space. Does that make sense? All right, so here's the other interesting data point with sampling. And what this chart is showing is that there's a speed to accuracy trade-off. And the x-axis really represents the sample size, but it's equivalent to saying my data size itself. Right? So the interesting thing is that when my data starts to grow, my error rate for my queries with samples essentially exponentially starts to drop, right? To a point where, if you see here, I mean, even if I go from here to doubling my data size, my error rate has marginally decreased only, right? So the nice thing in sampling is that, when my data sets are rather very, very large, I can use my fraction to be smaller and smaller. It's like saying that if I had 1 billion records, maybe my sample needs to be, 50 million records. If my data set was 2 billion records, maybe I can still maintain only 50 million in my sample and still get pretty accurate answers. That's the general idea. Okay, so so what we land up doing is, it's not just about saying, okay, I get to sampling and I can produce answers. We have deeply integrated essentially this technology into the query engine and Spark itself. Right? So the way it works is that you can, whenever you run query, so if you look at this, we have extensions to SQL that allows you to sort of specify the error tolerance that you can have. In this case, saying error, I can tolerate a 10% error. There are other things like confidence interval and other things we've added. But by doing that, so what we land up doing is we essentially look at a query, and then we're able to quickly figure out by looking at samples as if they're indexes to say, hey, can I actually execute the query on the sample, but without looking at the full data set, I can actually compute how wrong my answer will be. Right? And anybody here is statisticians who knows about bootstrap and poisonized bootstrap? So we do a number of techniques to compute an error by simply looking at the sample with a very high degree of confidence, right? Using some of these algorithms. right? So once you compute the answer, and if my error looking at the sample is less than the constraint you have specified, guess what? I can just execute on the sample and return an answer to you, right? And if the answer is no, then I essentially have to look for the full table now, right? So that's kind of what we're doing. So the beautiful thing here is that in my system, inside Spark, inside Snappydata, you don't even need the full table, right? Leave the full table. Maybe it's sitting on S3, maybe it's sitting on HDFS, maybe it's sitting on my relational database, and I can still compute an answer, right? So of course, if I can't do the query you're asking, it's gonna, the penalty is gonna be much higher. So as an example, if somebody's asking a point query, right? Where is richest record, and my sample may not have that specific record you're looking for. Obviously, figure it out, send it to the real table, get an answer back. Right? The real table could be sitting in Snappydata, could be elsewhere. All right. So when just a laundry list of capabilities in our Synopses data engine, you can do uniform sampling, stratified sampling. We do other Synopses data structures for outliers. I mean, we're working on joins. So yeah, these are all sketching because you can't even do samples. You can't do like max and min. Can you give me the highest paid employee? You can't really do it right easily. My sample may not have picked it up. So we use other data structures to do like dot k and max min that sort of thing. All right, so let me see if I can switch to a quick demo. How many here use Zeppelin? Anybody? Oh, cool. All right, so. I'm using the on-time performance data for LLMs. I mean, who's used the on-time data for LLMs? So this is from the FA guys, right? I mean, you have the data for the last 20 years. I'm just using about 6 years worth of data. So what I'm trying to do here is I will load the full data set and keep it in a column table, right? See if I show you. So this is the load program, right? So I'm loading from Parquet, and I'll keep the full data set in a table, and I'll also create a sample, and then we compare the difference in performance and also the difference in accuracy by running the queries on both. Right? So this is just a straight up Spark program, right? This is using Spark SQL on the data frame API. So essentially, there's my data folder that's got Parquet. I mean, the data set is actually about 52 million records in Parquet, so essentially I union it about 4 times, so I can get about 200 million records, right? And then I register that data frame as a table called airline. So the airline table now represents the full data set, right? And then, as you see here, using a simple SQL statement, I create what we call as a sample table. That's got a bunch of options in it, right? And so this thing called QCS, which says query column set, really represents the stratification that I want from a sample, right? And the fraction says, how small, how big should the sample be? Then I have a dimension table. The dimension table gets replicated across all nodes, so that if I do a join, it becomes localized, gives us much higher efficiency. So as you see here, I'm just doing a count star on airline. It's about 210 million records. I do the exact same count star on airline, but I add this additional clause that says I can tolerate an error of 10%. And if you look at the result, I mean, there's 210 million records, even though the actual count inside that sample is only 2.1, but it's about 1%, right? Sample. And we have this special thing that says if you go sample underscore count, we give you the actual count inside the sample. So now you can see all sorts of, you're essentially now starting to do analytics, right? You're exploring your data sets. So you can see, hey, which airline had the most flights in my data set? The one on the left, I executed concurrently. In other words, I executed a whole bunch of queries concurrently, right? So it's a rather straightforward query, right? It's a simple join with a group bar, and then I'm essentially saying, give me the top 8 airlines with the most number of flights. I'm doing the exact same thing here. This guy took 107 seconds, right? We execute, when I was executing a bunch of queries concurrently, and the exact same query where I said I tolerate a 1% error, came back in 2 seconds, right? It's a huge whopping difference. And the other nice thing is that if you look at the memory utilization here, it's literally just 100 megabytes to store 210 million records in my sample, versus actually the full table will be several gigabytes, right? So I have a whole bunch of questions like that, right? I mean, you can Keep asking questions. And the nice thing is that when you go and specify an error, and we cannot do it, right? In other words, given the data set I have in a sample, the error rate is going to be high, it'll automatically send that question over to the real data set. I can show you. Let me see if I can switch over. Okay, so here is there is another example. This is actually running in AWS. So it's the New York taxi data set that's available, so we're analyzing that. So one of the nice things I wanted to show you quickly was, so we do this thing which we call instant visualization, right? Assuming I'm connected, I should be able to run this thing. So if you look at this query, right, I mean, we have this directive that says, show me approximate results first, and this query looks exactly the same as this query. And what I'm trying to find out is, how long does it take to take a ride from Midtown Manhattan to downtown for various hours in the day, right? And as you'd anticipate, I mean, it's pretty low after midnight or whatever, and then it starts to climb up and really peaks at about 5 p.m. and 6 p.m. Right? So if you look at this answer, it's pretty much the same. So if I run the query, let me just clear this thing. So the sense, hopefully it runs. So if I run this thing, right, it immediately provided an answer, and on the background, it's now executing the query on the full data set by going to S3, pulling the data and doing this thing, right? So when I provide the answer, if you can see for this query, it's a very pointed query given my data set in the sense that I don't have too many data points from midtown to downtown in this data set. So my error rates are in fact high, right? So in a number of situations, you're saying, yeah, give me an immediate answer so I can get a feel. But maybe the insight you're looking for, you have it. In other words, you're saying, what is the average time, right? At like 5 a.m., it's about 15 minutes or whatever, right? And you can cancel that query. That's the nice thing. You can cancel a very, very expensive thing right away. But what has happened here is that in the background, it executed back. It essentially swaps Zeppelin. So we had to make some changes in Zeppelin. Check it back into Zeppelin. So yeah, the sample thing took about 900 milliseconds. And the time to execute the full table query was about 24 seconds. Okay. We are in about a week or two. We have merged with Spark 2.0 based distribution. We're going to release. We're going to offer a free cloud trial. So anybody, if you're interested. If you have data sets you work with, relatively large, or what have you, can sign up. We'd love to get some feedback, right? You just sign up and get a free cluster and right up. Okay. So you can, of course, if you can send a mail to Charm or Snappydata, take care of that. So with that, I'm just gonna stop. Entertain more questions. Anything else? Okay. But
The question, so just now the demo, so you're doing OLAP on a single table. So I would imagine if you have, say, in a single query, OLAP query, you have multiple table joins, and I specify the error, say 10%. But is that each table 10% error, or combined for the whole query?
Right. So the question is, what happens if I work on multiple tables and I provide an error percentage? So the error really doesn't apply to tables at all. It applies to an answer, right? What I'm basically saying, if you look at this answer, that's why there's a thing called error bar, right? So if you look at this, let's actually go ahead, keep it in tabular form. So if you look at this query, right? So this query resulted in one answer for every hour of the day, right? So there are 24 essentially answers, right? So what this guy is essentially guaranteeing is that, hey, what kind of error tolerance can I afford for each and every answer here? So when I go 10%, every single answer here has to be less than 10% in error. So it's nothing to do with the table, it is more to do with the answer, right? Because that's the only thing that's meaningful for you, right? You're consuming an answer and saying, is it like within at least 90% correct?
I mean, each row in.
Yeah. So if I were to run this query, the thing is that I would say that there's an absolute error. So we have built-in functions you can actually compute and say, what is the absolute error? What is the relative error? I mean, there are bunch of built-in functions that you can use to get that data out. Any other questions?
Can you go back to the other demo you were showing earlier, making the dimensional table to be
Replicated?
replicated?
Yeah. So let me go back to this data set. Yeah. So essentially, if you look at this, there's a whole. Let me actually show you the syntax. I mean, you can actually look at this, right? So essentially, I'm creating a first staging table because the data is in Parquet format. So just an external table. Then from the external table, I create this thing called inline reference using this thing called row. It's a built-in data format type. So we have using row, using column, using Parquet, using JSON, and all those things. So that's a standard. The syntax essentially follows exactly what Spark SQL gives you, right? And so you're familiar, I mean, like if let's say I'm hitting Cassandra, right, and doing this, you would have using, the Cassandra's data source connector, and then you provide options, and the options is up to the provider, right? So the using syntax essentially says who's the provider. In our case, given that we're fused into Spark, you can just say row or column, but in a sense, it's like saying, give me the snappy row table, give me the snappy data column table. That makes sense? So the options are, so let me actually switch to my slide there. I didn't really cover any of the stuff on the Spark side, but it really looks like this, right? So you go create table. So by the way, this is exactly a Spark SQL syntax, right? So what Spark SQL allows you to do, because it's extensible, is that it allows you to specify options. So the options is up to the provider, right? So the using clause essentially has the provider list. So it can be JDBC, row, column, Parquet, a bunch of providers. So if you go row, some of these options apply. If you go column, some of these options apply. These options that you see here, they're very specific to Snappydata. Right? So for instance, we can say, hey, when I create table orders, make sure that orders actually can be co-located with customers, right, as an example. The other thing is that, hey, I want to specify how you partition your data set. Or I can say it's a row table, and hence I want it replicated redundancy level. So you can specify saying redundancy 1, 2, whatever. But by row table, by default, is actually replicated. So if you didn't have any of the options, we literally assume that the table you want to create needs to be replicated across nodes. Then on the fly, create the replicas. So if you add a few more nodes, well, you get more replicated replicas of that dimension table.
So if you specify the row, the entire table gets
Correct. Unless until you say I want to partition it.
then
Correct. Yeah. Yes. One more question. I'm going to stop. Okay. All right.
How would you compare this product stock versus like how you
Right. Yeah. Good question. Right. How would Snappydata, which is like a database engine, if you may, used with Spark, compared to a true MPP database, that's Vertica, Visa. So there are. Okay, let me finish this question. So the first thing is that we're big believers in Spark and the flexibility Spark offers. Right? And the nice thing with Spark is that it's not just about saying I can run SQL. It's about being able to do native transformations in Python if you wanted to. You can run a streaming job, and the streaming job is now fused with what you can do inside a relational engine, right? You can work with objects as object RDDs or data sets very, very nicely. And you have all these rich APIs, whether it's just graph libraries or the machine learning libraries that are evolving so rapidly. So those are the advantages we are piggybacking on. That we think that the ecosystem with Spark is so rich, so diverse, and will continue to grow. Thanks a lot, guys. Appreciate it.
So guys, thanks once again for coming. I'll post the slide and video in a couple of days. Thanks again.